This is a diamond, a 580 carat diamond, and they grew it inside this machine. Most people think about diamonds for jewelry, but everybody's missing what's most exciting happening right now. We've built giant machines that can recreate the inside of the earth to grow diamonds and found brand new ways to make them, which is now unlocking the hidden potential of what turns out to be an incredible super material. Diamonds are crazy. They're sending diamonds into space, adding them to massive computers, and using them to try to solve one of the biggest technological problems we're about to face. This story is about pushing the limits of material science to benefit all of us. In this video, we're getting rare access inside a lab where they make diamonds.
Oh, it's starting to happen.
And we're shrinking down inside a computer to show you
Why diamonds are not what you think.
Diamonds.
Lab-grown diamonds.
They're not real diamonds.
We're reaching the limit.
We need more compute.
The future of diamond is very exciting.
Excuse me while I just hold a fistful of diamonds. Oh my God. This is so cool. Look at all these machines. They're making diamonds in every single one of these.
if you wanted to see where a natural diamond is made, you'd have to drill a hole way deeper than you think. Most other gemstones, emeralds and sapphires and rubies, form here in the crust. But diamonds come from here, inside the mantle. This extremely hot, goopy, liquid rock is filled with carbon atoms that are squeezed together over millions of years by pressure 50,000 times what it is here on the surface, forcing them closer and closer until they form bonds with 4 of their neighbors and become... This structure is what makes diamond not just the hardest natural material we know about, but 4 times harder than the next hardest material. And it's why we've already been using diamond for decades to cut and drill and grind and polish, because diamond can cut through basically anything. But wait, that doesn't look like a diamond. When you think of lab-grown diamonds, you probably think of this. This is a single crystal diamond. It's the kind that gets cut and polished into jewelry.
So that's grown in our chambers, and over several weeks of time, that little seed is converted into that big rough, and that might end up being a 2 or 3 carat finished gem.
Excuse me while I just hold a fistful of diamonds. Wow.
Be very careful. See these little crystals?
Yeah.
They're sharp.
So one of the things they're telling me is that the edges are very sharp. So I'm going to blow these little fragments off of my hand so they don't get, embedded in my skin. So now I've got dangerous diamond detritus on my hands.
Diamonditis.
I've got diamonditis. Thank you. So this is what people might be most familiar with if you know about lab-grown diamonds. This one is a very different thing. What am I holding here?
You're holding a piece of polycrystalline diamond.
Instead of growing one single crystal, they grow millions of tiny diamond crystalates that bond together, each diamond being only about the width of a human hair. But this particular diamond wasn't made for cutting or polishing. It was made for something very different, a hidden superpower of diamond that most people don't know about.
So I've got this razor made of stainless steel, very sharp razor. If you put a razor on an ice cube, you can cut it, but I'm pushing into it, it's gonna take a while. You take diamond, do the same thing. Ready? Oh my God.
Look at that! That diamond cuts ice like it's butter. And this has nothing to do with it being super hard. Instead, it has to do with the incredible way that diamond handles heat. The bonds inside a diamond are short and stiff, but the atoms can still vibrate. And when one atom jostles its neighbor and that one jostles the next, the ripple travels through the crystal, moving heat. And heat can travel incredibly quickly through diamond. Exactly how fast is called its thermal conductivity. And if you look at a chart, here are other popular materials used for their really great thermal conductivity. Now guess where diamond is. Here. Diamond moves heat better than almost any other material on Earth. So that's why this diamond can cut ice like it's butter, because it's stealing heat from my hand.
It took all the heat from my hands. They're so cold.
Okay, so diamonds are insanely good at stealing heat. Why does that actually matter to me? It's time to jump into a computer. Hello? So, you know when you're doing something really intense with your computer and it gets very hot? That's a small example of a much bigger problem that's holding back basically all of our cutting-edge computers today. And that's because most of what's around me right now is made of silicon.
Silicon.
The Silicon Valley.
The backbone of computing.
Silicon is what makes up the on-off switches that run basically all modern computers. Transistors. More transistors, more processing power. And we've been able to make transistors unbelievably small. This is one of the most unbelievable stories about modern technology. It is just incredible what we've been able to do. Okay, ready? If this is the size of the first iPod, then this is the size of the first transistor. But today's are so much smaller. This is the smallest species of ant. It's only 1 millimeter. And this is the size of one of my favorite animals, the tardigrade. But now it gets crazy. The smallest human cell is the red blood cell. But we need to keep going. Even smaller than the size of bacteria. This gets us to the size of the transistor in that first iPod. It's about as big as a flu virus. This is the size of the transistors in the first Nintendo Wii. But we still need to go smaller. If we keep going all the way down, this is about how small today's transistors actually are. This incredible ability to make transistors smaller has allowed engineers to roughly double the number that they can fit onto a chip every 2 years. You might have heard of this. This is called Moore's Law. It's why your pocket-sized phone is over 100 million times faster than the computer that landed us on the moon. But we seem to be hitting a wall. If transistors get much smaller, physics tells us we won't be able to control how they switch anymore. So instead of packing more transistors side by side, like cramming more houses into a neighborhood, they've started stacking them, like multi-story apartments instead of single-family homes. But this generates a lot of heat and nowhere for it to go. And this extra heat is a big problem. All of the better futures that we dream about, powered by more computing, more people in space, or better cars, or better medicines, or cleaner energy, they all rely on finding a way to overcome this heat problem. And now they think that diamonds might be able to help.
We want more speed, we want more performance, more functionality, and all of that is exercising a humongous pressure on the electronics.
That is one of the world's leading researchers in using diamond blankets to cool the inside of computers so that they can run faster and do more using less power.
We are packing things down into smaller and smaller, and the more you compel them to run faster and harder, the more heat you are generating. And that is making things less efficient until it all falls apart.
All computers need to get the heat off the chip as quickly as possible. That's called heat spreading, and find somewhere to dump it, a heat sink. Inside your computer, when it makes that noise, what's happening is your chip is generating heat, and copper on top is trying to get it off the chip and spread it out, and send it through copper pipes and dump it into a bunch of aluminum fins, until the fan that you're hearing blows across the fin's large surface area to finally carry the heat out of the computer. This is a small problem in your computer, but a really big problem in data centers and electric cars and satellites. But what if we could use an even more thermally conductive material like
Diamond seems to be the right material.
The idea is to grow diamonds right onto chips, like a blanket that helps steal the heat away much faster.
And what our work showed is that if I wrap it around like a blanket, you can make those transistors run cooler, hence way more efficient than otherwise it would be.
But you can't do that with natural diamonds. Not just because getting it out of the ground is so expensive, but because many have trapped pieces of other elements when they formed that make them worse at moving heat. So the only way that this could work, the only reason they're exploring this right now, is because we've gotten unbelievably good at growing super pure diamonds. And how they do it is wild. So on my way to the diamond lab, I was researching the first time that anyone ever grew diamonds. And I found all of these really cool released CIA documents about it. So I started writing the next part of the script, but I really didn't want anyone looking over my shoulder and seeing what I was doing, which is why I'm using this for privacy. Most companies do this with a plastic filter that you stick on, basically polarized sunglasses, but for your computer. And that works, but it cuts your brightness in half and I lose them constantly. But in this device, there's another layer hidden inside the display, thinner than 3 human hairs. And when I click this button, extra voltage causes the molecules in that layer to tilt. So light going straight forward toward me passes through clean, but light headed sideways to the nosy person right there doesn't. And it's super easy to turn off and on. I travel a lot on this show, and it makes a really big difference to have features on a commercial device that work the way that I work. If you want to check it out, go to this link. Now let me show you these documents, because the first time anyone ever grew a diamond was in a secret project after World War II. Released CIA documents show that the US needed about 5 million carats of diamonds a year to grind and drill and cut parts for airplanes and tanks and armor. So General Electric's research lab set out to try to make them. They called it Project Super Pressure because they were using a giant machine, similar to this one, that creates conditions like the inside of the Earth. It works by taking a super pure carbon powder, adding metal flux, and then heating it up to over 1,000 degrees Celsius to create a molten mix like in the mantle. But instead of using the weight of the Earth, this machine uses powerful arms to squish it together, creating pressure that's equivalent to placing a commercial airplane on your fingertip. But all that pressure and all that heat won't make a diamond unless you have this. A tiny little diamond that acts like a seed, giving the carbon atoms something to grip onto. And this speeds up the growing process from millions of years to under a week. And they cleverly called this method high pressure, high temperature. But today, they often use a machine like this with an even newer method. And now they're gonna let me grow a diamond.
Time to grow a diamond.
It's kind of like baking a cake.
First ingredient. Just like the high pressure, high temperature method, we use a diamond seed, telling the carbon atoms what molecular structure to form. And instead of placing it between giant arms, you place it on this heat-resistant metal puck, and then you stick it into this chamber.
I'm gonna click Start Process.
The first thing they do is pump out all of the air from the chamber. That way they can add in only the ingredients needed to make a pure diamond. First ingredient, hydrogen gas. That's what's gonna help build the crystal. Then they turn the chamber into a large, powerful microwave.
So it's 10 times as powerful as the microwave you would have at home.
These microwaves give hydrogen molecules energy, creating a cloud of plasma gas that can break apart molecules.
We're gonna see the plasma when it starts in 3, 2, 1. Cool. It's beautiful.
It's very cool.
Look, there's the plasma, and that's the puck that we put in where the diamonds are gonna grow. Now, final ingredient, you need carbon, and you get it by adding methane gas, CH4.
When the methane gets added, you're gonna see it change color. It's gonna be really cool. Oh, it's starting to happen. You can already see it turning green. Oh, yeah, there it is.
The energy in the plasma breaks apart the methane into carbon and hydrogen, and over time, the carbon atoms deposit onto the seed and the crystal grows. They cleverly call this method chemical vapor deposition. And if they keep the conditions just right for weeks, you get these. These are the kind of diamonds you can cut up into gems, but to grow this kind, you don't even need a seed.
There she is. A newly grown diamond.
These are all diamonds, but they're also basically just microwaved methane and hydrogen. These lab-grown diamonds are even more pure than the ones found in the Earth, making them better at moving heat. And we can grow them into any shape that we want. And this process of growing diamond has gotten so fast and so reliable that now experts say
Every chip having a diamond layer is not a sci-fi kind of outlook. I think it's very real. It's very possible.
In fact, there are already data centers using diamond-cooled servers right now.
In fact, the world's first diamond-cooled server was an NVIDIA H200.
And look up, because there are diamond-filled satellites in space.
It's helping to shrink the size of satellites. A large portion of satellites is designed for the electronics and the managing the heat.
Diamonds in data centers in particular could be a big deal if they mean you can get way more with way less. And it does seem like they can.
This is incredible breakthrough news. This is hot off the press. By the way, we just got this data last week. This recent test that we just did in a data center in San Francisco actually doubled the amount of compute coming off a GPU.
Again, just to be really clear, this is all a test. It's a big experiment. It's huge if true, right? It implies a future world with fewer data centers for the same power.
Instead of building 2 regular data centers, you can build 1.
Today's applications is craving for 2 degrees C reduction in temperature. Some of our work has shown that we can take it down by 70 degrees C.
And beyond more efficient data centers, Diamond has more hidden superpowers that people are just beginning to scratch the surface of. Get it? Because you can't never mind. Like its incredible ability to handle extremely high voltages, which could, in theory, mean really good diamond transistors. Or its resistance to radiation, which makes Diamond really useful in space and in massive experiments here on Earth. And even its compatibility with our human bodies, which makes Diamond promising as a drug delivery tool, which are all just huge if true.
I am really so excited about this.
To be really clear, we don't know if true yet. It's a really exciting moment for material science. No one knows exactly what role diamonds will play in our computing future. We're figuring it out right now. That's what makes this so exciting. It's a big experiment, using something that we know for jewelry for something much bigger. Because we figured out how to mimic the inside of our planet to make something that only nature could make before, using tech that's now gotten so good that we can explore new ways to use it to benefit humans and the planet that made it in the first place. If you believe in optimistic science and tech stories, subscribe.